Ladies and gentlemen, this is the Prelab video for your solution stoichiometry lab. This is where I'm going to talk about the concept of the job plot, but also how we're going to use the job plot in this particular lab to answer the fundamental questions. So first up, all about the job plot. What is it? Fundamentally, a job plot is a very specific type of graph based on a very specific type of experiment or lab investigation that is used to determine molar ratios between reactants or products. So it's essentially a perfect stoichiometry tool because it can tell you the molar ratio between two elements in a compound, and it can also tell you the molar ratio between two compounds in a chemical reaction. So you can use it depending on what your needs are to figure out either subscripts or coefficients. And it's a way for determining these things experimentally. Let's say you don't have percent composition data to do an empirical formula problem. Let's say you don't have formulas, so you can't balance the chemical reaction. If you need to figure out those ratios experimentally, the job plot is how you can do that. It's a way of figuring out molar ratios. The basis for the job plot is that you don't know what the correct ratio between two things is. In this case, in this particular lab, we're looking at molar ratio between two compounds. So we're talking about coefficients. So what you do in a job plot experiment is you experiment with ratios. You do a whole bunch of different trials where you're varying the ratio of, in this case, the two reactants to one another. You might run a trial where they are in a ratio of 5 to 1, where they're in a ratio of 4 to 2, and then 3 to 3, 2 to 4, and 1 to 4. So you vary the ratios. You get a whole bunch of experimental data that's got different ratios of, again, as in this case, reactant to reactant. But you don't just react them together in various ratios. You also have to measure something. And the key is that you measure something about a product in each time, each case. You measure, and there are different ways to measure products. The example that's given in your lab handout is you're measuring the mass of a product. That's actually not what we're measuring in this particular lab, but we're still measuring something fundamental about the product of the reaction. So for each trial you're recording, when I did the 5 to 1 ratio, how much product did I get? When I did the 4 to 2 ratio, how much product did I get? You're looking at how much product is produced for each of the various ratios that you've experimented with. And what the job plot, and then you graph that information. It is a plot after all. You are creating a graph. But what that information is used for is right here. The ratio of the trial that produces the most product is considered to be the actual correct molar ratio. Because when you're producing the most product that you possibly can, that means that your reactants have to be in the correct molar ratio to one another. That's the only way that you're going to get the most possible product. If your reactants are not in the correct molar ratio, then that means that you're going to have too much of one and not enough of the other, right? Because they're not in the right ratio, so you've got too much of one and not enough of the other. That means that one of them is going to be limiting, and it will limit how much product you can actually make. But when you've got your reactants in the correct molar ratio, then you're going to be able, your product is going to be as close as possible to the theoretical yield, to as much as you theoretically should be capable of making. We know we're identifying the correct ratio because that's when the most product is going to be produced. It means that we've got those reactants in the ratio that they're meant to be in. And when I say the molar ratio here, this is typically done by controlling the concentration of the solution. That's what we're doing in this particular lab. We know that everything is 0.1 molar, we just don't know what it is. So that's sort of our in for making sure that for controlling the mole aspect of it. Okay, so this is the idea. This is the fundamentals behind a job plot. You experiment with different ratios of reactants to one another. You measure how much product is produced, and whichever ratio produces the most amount of product, which you might have to interpolate or extrapolate based on the data that's present, that ratio that produces the most product is the actual molar ratio in the question for the two reactants. Now, creating the job plot. This is the example job plot that's from your lab handout. X-axis, Y-axis. We always put the independent variable on the X-axis, the thing that you are changing, and the dependent variable on the Y-axis. The X-axis is the thing that you have control over in a job plot is the amount of one of the reactants. So you are choosing, in this case, you're choosing to control the amount of iodide that's in the reactant. In the lab that we're doing, you're going to be varying. You could put either the sodium hydroxide or the unknown acid on the x-axis, the thing that you're changing. Reactants on the x-axis, that's critical. On the y-axis, some measure of the amount of product. So the y-axis is where you're putting that amount of product that you're measuring about the reaction. So in this particular reaction, it was lead plus iodide goes to a precipitate. And they were trying to figure out what the formula of the precipitate was. So as you can see, they've got the precipitate, which is a product, on the y-axis, and the iodide is a reactant on the x-axis. So you're putting your reactant, which you're controlling, on the x-axis and the product on the y. And what you're seeing, each of these individual data points is a trial. Meaning they did a reaction. Every single time you see a data point, they did a chemical reaction and they measured the amount of product that they got. What you're seeing, what's not being shown, is that, for example, let's see right here, this was 2 grams or 2 milliliters, excuse me, of the iodide. They also had 8, I believe, no, I think it was actually 18 milliliters of the lead. So they were reacting this at a 9-to-1 ratio. And what they're seeing right here with this very first point is that at the 9-to-1 ratio, you're not getting the maximum amount of product possible. They only got like 0.29 grams or so of the precipitate. So each of these points is an actual trial, and each of them represents a different ratio of reactants to one another. They take this information, as you can see, and they just plot all of the points. And there are always going to be 2 lines in a job plot, a line that goes up and a line that goes down. For the line that goes, for both when the line is going up and when the line is going down, aka right here and right here, one of the reactants is limiting. And again, over here, one of the reactants is limiting, but now it's actually the other reactant is the limiting reactant. But this point, the point where the 2 extrapolated lines intersect, neither reactant is limiting, because we have the correct molar ratio. Because right here, this is theoretically the most product that we can make. And you can then figure out how much lead and how much iodide were needed to make that theoretical maximum amount of product. And whatever the ratio between the lead and iodide is when we're making the most product, that's the correct molar ratio, and you've figured out the stoichiometry of the reaction. The job plot that we're going to be constructing, so now this is making it specific for our particular reaction. The reaction that we're doing is written right here. NaOH plus unknown acid goes to water plus salt. But you don't know what the unknown acid is. I'm not giving you the formula of the unknown acid. What you're going to work out for me is, what's the ratio? Is it a 1-to-1 between sodium hydroxide and the acid? Is it a 2-to-1? Is it a 2-to-3? Is it a 3-to-1 ratio? Essentially, you're figuring out the coefficients of this equation, despite the fact that we do not know the formula of the unknown acid, and therefore we cannot know the formula of the salt. The key is that I am telling you that the reactions we'll be looking at are exothermic. And if you remember, exothermic means that heat is produced, therefore heat is a product. this is really handy because the salt that we're making, it will be a soluble salt, and water there's already so much water present because it's an aqueous solution. So measuring the product, because we have to measure something about the product of a reaction in a job plot. We can't really measure the water, can't really measure the salt. Well, we could, but it would be difficult. It would be much more difficult. But we can measure the heat. We can measure how much heat is produced. So by measuring the temperature change associated with these different ratios of the NaOH to the acid, we're going to determine when the most heat was released. When, based on the various ratios that you're looking at, when did the reaction produce the most heat? And whenever the reaction produced the most heat, it's right here. That point where we have the most heat, it would be equivalent to the correct molar ratios between the sodium hydroxide and the unknown acid. Now, this is fundamentally a calorimetry problem because we are going to be measuring heat. So we are going to be using a simple coffee cup calorimeter. Coffee cup calorimeters are really, really simplistic. It's funny that they're even given such a fancy name, but it's literally just two coffee cups nested together, not just one, it's actually two. You do need them both. And then you put them in a beaker, and the beaker is essentially for stability. And that's it. The styrofoam holds in the heat that's released by the reaction. Again, this is an exothermic reaction. And it keeps it in so that we can actually measure the heat. Because if the heat was being lost to the surroundings, then we would kind of be missing how much product is being created. I'm going to pause the video here because I'm just breaking it up into two sections. So this is going to be part one. And then please actually watch part two. I'll continue to talk a little bit more about the particulars of this lab, this Prelab.